This module focuses on the practical application of strategies to cool urban environments and reduce heat stress in cities. Urban areas are increasingly affected by elevated temperatures due to the urban heat island effect, where dense buildings, paved surfaces, and limited vegetation trap heat. By exploring real-world examples, this module demonstrates how thoughtful interventions in vegetation, shading, surface materials, and urban design can meaningfully improve thermal comfort for residents and visitors alike. Practical examples illustrate the tangible impact of these strategies, moving beyond theoretical concepts. For instance, the introduction of street trees or green roofs not only reduces air and surface temperatures but also enhances walkability, aesthetics, and biodiversity. Shaded corridors, high albedo pavements, and water features show measurable reductions in heat stress at microclimate scales, improving comfort for pedestrians, children in playgrounds, and outdoor workers. The module emphasizes evidence-based approaches, showing how data on temperatures, humidity, and human-perceived heat can guide urban planners and designers. By connecting planning choices to measurable outcomes, the study highlights the importance of integrating multiple interventions across different urban scales, ultimately creating more livable, resilient, and climate-adaptive cities. This slide emphasizes why the chosen case study is important for understanding and applying urban heat island (UHI) mitigation strategies in a real urban context. By examining a specific site, the study demonstrates how site-specific factors, including vegetation cover, surface materials, urban form, shading, and water features, directly influence thermal conditions. It shows how localized interventions can reduce heat stress, improving comfort for people, particularly in areas where exposure to sunlight and high surface temperatures is significant, such as playgrounds, streets, and plazas. The case study also highlights critical practical considerations for planners and designers. These include the scale of interventions, cost implications, maintenance requirements, and feasibility within the local urban fabric. Not every strategy is equally applicable everywhere, so understanding how to adapt solutions to local conditions is essential. Ultimately, the case study provides insightful guidance and inspiration for urban design. It demonstrates how careful integration of vegetation, shading, surface materials, and design interventions can transform hot, uncomfortable urban spaces into cooler, safer, and more livable environments, while also supporting long-term climate resilience and public health goals. This case study highlights a highly practical and important finding for urban design. Playgrounds exposed to full sun can become significant thermal hotspots, where temperatures rise rapidly compared to surrounding areas. In these spaces, surface heating from asphalt, rubber, sand, or other materials can elevate local temperatures enough to push children from normally comfortable conditions into levels of serious heat stress, even on days when the broader urban environment remains tolerable. This demonstrates that microclimatic conditions can differ dramatically within small urban areas, emphasizing the need for targeted interventions at the pedestrian scale. Research shows that shading, particularly from natural tree canopies, plays a decisive role in mitigating these risks. Trees not only block direct sunlight but also cool surrounding air through evapotranspiration, providing both immediate surface shading and localized air cooling. Artificial shading, such as shade sails, can also help, but their effectiveness is generally lower and may lack the added benefits of natural vegetation. These findings underscore the importance of carefully considering playground orientation, surface materials, and vegetation in urban design to protect children from heat stress and ensure safer, more comfortable outdoor environments. The methods used in this case study were straightforward yet robust, providing reliable insights into microclimatic conditions experienced by children in playgrounds. Field measurements were conducted directly within the playground areas, focusing on both surface temperatures and air temperatures at heights and locations corresponding to where children interact with the environment. By measuring at child height, the study ensured that the data reflected actual thermal exposure, rather than relying solely on adult scale or ambient measurements, which can underestimate heat stress experienced by younger individuals. To evaluate thermal stress, the study used well-established bioclimatic indices, including the Universal Thermal Climate Index, UTCI, and Physiological Equivalent Temperature, PET. These indices combine air temperature, humidity, wind speed, and radiation to quantify human-perceived heat, providing a more accurate assessment of discomfort and potential health risks. Additionally, the study compared different surface materials and shading types, such as natural tree canopy versus artificial shade sails, to determine their relative effectiveness in cooling playground microclimates. This approach allowed researchers to link design interventions with measurable changes in thermal comfort, offering actionable guidance for urban planning and child-focused public spaces. The key results of the study provide clear, actionable insights into effective strategies for reducing thermal stress in playgrounds. Among all interventions, tree shade proved to be the most effective, reducing heat stress by up to 2 full levels on thermal indices such as UTC-I or PET. This significant reduction reflects not only the shading effect but also the additional cooling provided by evapotranspiration, which lowers surrounding air temperatures and improves comfort for children at ground level. Artificial shade sails also contributed to reducing thermal stress, but their impact was generally about half as effective, typically improving conditions by 1 index level. While they provide quick and flexible shading solutions, they lack the full cooling benefits that natural vegetation offers. The study also highlighted that natural ground surfaces, such as grass or soil, do not automatically result in better thermal comfort. Their cooling effectiveness depends heavily on soil moisture, maintenance, and local microconditions, meaning they cannot be assumed to provide consistent relief under all circumstances. These findings underscore the importance of combining strategic vegetation, surface materials, and shading to maximize thermal comfort and safety in playgrounds. From a design perspective, the study provides very clear and actionable guidance for creating safer and more comfortable playground environments. The most important recommendation is to prioritize tree planting and preserve existing tree canopy near playgrounds, as natural shading consistently reduces surface and air temperatures while also improving thermal comfort through evapotranspiration. Trees offer long-term benefits, including cooling, aesthetic value, and biodiversity support, making them a cornerstone of effective UHI mitigation in child-centered spaces. Artificial shading, such as shade sails or canopies, can serve as a useful short-term or supplemental measure, particularly where tree growth is slow or space is limited. However, they should ideally complement a natural shade strategy rather than replace it. The study also emphasizes the need for child-scale measurements, recognizing that children experience microclimates differently from adults due to their height, activity levels, and interaction with surfaces. Additionally, moisture management of soils and vegetated surfaces plays a key role, as adequate hydration enhances the cooling benefits of plants. By combining these strategies thoughtfully, urban designers can create playgrounds that are not only visually appealing but also safer, cooler, and more resilient to extreme heat. This study demonstrates the value of local climate zones, LCZs, in understanding temperature variation within urban environments. By classifying the city of Hradec Králové into LCZ types, researchers could systematically compare densely built areas, open spaces, and vegetated districts, revealing patterns of heat accumulation and cooling potential. Compact, intensively built LCZs, particularly mid-rise and low-rise categories, tend to store large amounts of solar radiation, contain minimal vegetation, and often have restricted airflow, making them thermal hotspots during summer. These areas experience prolonged heat exposure, increasing thermal stress for residents, especially vulnerable populations such as children and the elderly. In contrast, vegetated LCZs, including parks, gardens, and urban forests, benefit from shading, evapotranspiration, and moisture-retaining surfaces, which lead to significantly lower land surface temperatures, LST. While LST highlights stark contrasts between built and green zones, air temperature differences at pedestrian level are usually more subtle, as atmospheric mixing, shading, and urban geometry moderate heat exposure. By combining LCZ classification with temperature measurements, urban planners can identify priority areas for interventions, targeting both public health improvements and enhanced thermal comfort in the most affected neighborhoods. In this study, the city was systematically classified into local climate zones, LCZs, using a combination of remote sensing data and GIS-based mapping techniques. This approach allowed researchers to differentiate between compact, open, and vegetated urban forms, creating a standardized framework for comparing thermal behavior across distinct urban types. By categorizing areas based on building density, height, surface materials, vegetation cover, and land use characteristics, LCZ mapping provides a clear understanding of spatial variations in heat accumulation. Satellite-derived land surface temperature (LST) data was then used to identify patterns of surface heating and locate urban hotspots during summer periods. LST measurements reveal which surfaces absorb and store heat most intensely, highlighting the areas most affected by the urban heat island effect. To ensure that these remote observations reflected human-experienced conditions, ground-based air temperature measurements were collected at pedestrian height. These measurements validated satellite data and provided a more accurate picture of the thermal environment experienced by people, particularly in areas where exposure to heat could be high, such as streets, squares, and playgrounds. Mapping local climate zones (LCZs) provides critical insights for urban planning and climate adaptation, allowing city authorities to identify areas most at risk from heat stress and to target interventions efficiently. Compact, built-up LCZs, characterized by high building density, minimal vegetation, and limited airflow, can be quickly recognized as priority zones for cooling measures. Such interventions may include the introduction of green spaces, reflective materials, and strategically designed airflow corridors to improve ventilation and reduce heat accumulation. Conversely, vegetated LCZs, including parks, forests, and green corridors, naturally act as cool islands, providing localized reductions in both surface and air temperatures. Protecting existing green areas and expanding vegetation in urban neighborhoods enhances overall thermal comfort and contributes to biodiversity and ecosystem services. A combination of satellite LST data and ground-based air temperature measurements gives a comprehensive understanding of heat stress across the city. LST reveals where heat is stored in urban surfaces, while air temperature measurements show how the local atmosphere moderates this heat at pedestrian level. This dual approach ensures that interventions are both site-specific and effective, addressing thermal risks where they are most acute. For urban planners and climate adaptation specialists, LCZ mapping serves as a powerful diagnostic tool, enabling a systematic assessment of heat distribution and vulnerability within a city. By classifying areas according to their urban form, building density, vegetation cover, and surface types, planners can identify priority zones for targeted interventions, ensuring that resources are allocated efficiently and effectively. Compact, heavily built LCZs with limited greenery can be flagged as critical areas for measures such as planting trees, installing reflective surfaces, creating ventilation corridors, or introducing small-scale water features. Vegetated LCZs, on the other hand, function as natural cooling islands and should be preserved or expanded to maintain their microclimatic benefits. Their protection contributes to both surface and air temperature reductions, improves human thermal comfort, and supports urban biodiversity. Combining satellite-derived LST data with ground-based air temperature measurements provides a more complete picture of urban heat dynamics. LST identifies where surfaces absorb and retain heat, while air temperature at pedestrian level reflects the actual thermal conditions experienced by residents. This integrated approach allows planners to design precise, site-specific interventions that maximize cooling benefits and enhance the overall resilience of the urban environment. This study examined the health impacts of extreme summer heat in Czech cities during the years 2015 and 2016, focusing on the interplay between urban heat exposure and human well-being. By analyzing daily mortality records and comparing them with local meteorological data, the researchers identified clear associations between heatwave events and increases in deaths, particularly among vulnerable populations such as the elderly, young children, and individuals with pre-existing health conditions. These findings demonstrate that extreme heat is not merely an environmental concern but a serious public health hazard, with urban areas disproportionately affected due to the urban heat island (UHI) effect. The research showed that densely built urban zones, characterized by high proportions of impervious surfaces, limited vegetation, and constrained airflow, experienced higher heat-related mortality than surrounding rural areas. This confirms the real-world consequences of UHI, emphasizing the urgent need for urban planning strategies that mitigate heat exposure. The study underscores that understanding local microclimates and implementing targeted interventions can directly improve public health outcomes, reducing the risk of heat-related illness and mortality during increasingly frequent summer heatwaves. To assess the impact of extreme heat on human health, the study analyzed daily mortality data from multiple Czech cities, focusing specifically on periods classified as heat waves. These mortality records were compared against baseline summer mortality rates to identify excess deaths associated with extreme heat events. By establishing this baseline, the researchers were able to quantify the additional risk that heat exposure poses beyond normal seasonal mortality fluctuations. The study further correlated mortality patterns with detailed meteorological data, including daily maximum temperatures, heatwave intensity, duration, and the timing of peak heat periods. This cross-referencing allowed for a precise temporal link between heat events and adverse health outcomes, highlighting which days and conditions contributed most to elevated mortality. By combining mortality and meteorological data, the research provided a robust quantitative framework for understanding how sustained, high temperatures translate into human health risks. This methodology allows urban planners and public health authorities to anticipate vulnerable periods, identify high-risk populations, and prioritize interventions, ensuring that both preventive and adaptive strategies are data-driven and effectively targeted. The research highlighted that both the intensity and duration of heat waves play a crucial role in determining their impact on human health. Short, isolated heat spikes can increase discomfort and minor health risks, but longer, sustained heat events lead to more pronounced spikes in mortality, particularly among vulnerable populations such as the elderly, young children, and individuals with pre-existing medical conditions. The study showed that urban areas with high building density, limited vegetation, and large expanses of impervious surfaces suffered the most, as these environments amplify heat accumulation, slow nighttime cooling, and exacerbate thermal stress. Vegetated and well-planned urban areas, in contrast, mitigate some of the effects of prolonged heat by providing cooler microclimates, shading, and evapotranspiration. The findings clearly demonstrate that urban form, land cover, and surface materials directly influence how cities respond to extended heat events, affecting both air temperature and human-perceived heat stress. These results emphasize the need for targeted heat mitigation strategies, early warning systems, and urban design interventions that account not just for peak temperatures but also for the cumulative effects of prolonged heat exposure, ensuring public safety and comfort during extreme summer conditions. The findings of this study carry clear and actionable implications for urban planning and public policy, particularly in the context of rising temperatures and increasing frequency of extreme heat events. First, heat wave early warning systems are essential, allowing authorities to alert vulnerable populations, mobilize emergency services, and implement short-term protective measures. Such systems can significantly reduce heat-related illnesses and fatalities when paired with public health campaigns and community support networks. Urban design interventions are equally critical. Expanding and preserving tree cover, green spaces, and vegetated corridors can provide long-term cooling benefits, while reflective materials, shaded walkways, and optimized urban geometry improve pedestrian-level comfort. These measures help reduce both surface and air temperatures, mitigating the intensity of urban heat islands. Integrating health data with microclimate and UHI studies creates a robust framework for targeted interventions, enabling cities to prioritize resources effectively. By combining scientific evidence with planning tools, policymakers can implement strategies that enhance resilience, protect public health, and improve overall livability, preparing urban areas for increasingly frequent and intense summer heatwaves. The core finding of this study is that urban areas dominated by built and paved surfaces in Hradec Králové experience significantly higher heat stress, as measured by the humidex index, during hot periods. These areas accumulate heat more effectively and lack the cooling benefits provided by vegetation. In contrast, locations with abundant green space tend to remain more thermally comfortable, particularly during extreme heat events. The difference between built and green areas becomes most pronounced at high air temperatures, when heat stress poses the greatest risk to human health. At lower temperatures, however, the contrast is much smaller, indicating that urban form matters most during heat extremes. The study was based on long-term field measurements of air temperature and humidity collected at multiple locations across urban and suburban parts of the city. These measurements captured differences between areas dominated by built surfaces and those with more vegetation. Using this data, the researchers calculated the humidex index, which combines temperature and humidity to represent human perceived heat stress. This allowed them to move beyond air temperature alone and assess actual thermal discomfort. Finally, the frequency and intensity of different humidex categories were compared across surface types to identify which urban environments most often experience dangerous heat conditions. The results show that areas dominated by built and impervious surfaces experienced a much higher frequency of elevated humidex levels, particularly during heatwave conditions. These locations were more often associated with thermal discomfort and heat stress. In contrast, sites with significant vegetation cover remained cooler and provided more comfortable conditions for a larger portion of the summer. The most pronounced differences between built and green areas appeared during very hot periods, when heat stress reached critical levels. Green spaces therefore played an important role in maintaining lower or more balanced humidex values across the city. The study offers several practical design and planning takeaways for mitigating urban heat stress. First, maintaining and expanding green areas in the city is essential to reduce heat exposure and provide cooler microclimates. Second, urban planning should account for human perceived heat, using indices like humidex to assess thermal comfort rather than relying on air temperature alone. Third, the type of surface material such as paved, concrete, or vegetated has a strong influence on local microclimate and pedestrian comfort during hot spells. Overall, integrating vegetation and carefully selecting surface materials can meaningfully improve thermal conditions in cities. In this module, we explored several key strategies to cool urban environments. Vegetation provides natural shading and evaporative cooling. Material choices such as reflective pavements and cool roofs help prevent heat buildup. Urban form and ventilation corridors support airflow and reduce heat trapping, while water features introduce evaporative cooling and improve microclimates. The most effective approach is integrating these strategies so they reinforce each other. Together, they improve thermal comfort, lower energy demand, protect public health during heat events, and contribute to long-term climate resilience.